variety of sensing methods to reliably measure the switching loss of SiC and GaN devices in a small space. Presented by R.Nagahama from Iwatsu. Iwatsu has advanced power electronics measurement technology. Our main products are pH analyzer, curve tracer, and high-resolution digital oscilloscope probes. Today, we are going to talk about probes, especially how to reliably measure the switching loss of SiC and GaN devices in a small space. Measurements using probes in a switching analysis observes voltage and current waveforms and calculate the power loss, and that leads to the development of products with low power loss. An ideal probing condition is high impedance probes, the short wire, and the low common mode noise. However, in reality, the waveform is distorted, and the result of the power loss also causes a large error because of the wire length, the difficulty of probing in a narrow and small space, and the influence of an external electromagnetic field. For the SiC and GaN devices measurement, the phase of the voltage and current probes should be adjusted. Otherwise, the power loss analysis error will be increased. Please look at the pictures that the voltage and current probes are adjusted by our skew calibrator, IE1360. Please look at the schematic of the actual measurement circuit and its picture. In order to measure high voltage and high current, probes should be fixed by the 3D positioner, and the test circuit should be clamped by the skid for the safety measurement. The probe distortion will be an issue when measuring at high resolution. Distortion that could not be seen with 8-bit resolution oscilloscope appears as a large distortion with 12-bit resolution scope. In the figure above, 1 kV amplitude waveform was measured at 5 volts per division. The waveform is very clear. This can be called as matched waveform. The figure down below shows the mismatched waveform. This will affect the power loss measurement greatly. Even with a current probe, large distortions may appear. The figure on the left is a measurement example of current transformer, which is magnetic field detection type probe. The figure on the right is a measurement example combining a current transformer and the Hall element. When the current transformer and the Hall elements are combined, the waveform of the probe is distorted because of the inductance of the wire length of the current bridge used for current detection. 100 MHz Rogowski coil improves waveform distortion because its wire of the current bridge is short. Waveform distortion can be also improved with the differential Rogowski coil current probe method. The differential equivalent circuit is shown on the left. Even the common mode noise is superimposed, the noise is reduced, and a clear waveform can be captured. The waveform on the left is an example of single current probe measurement. The waveform on the right is an example of the differential Rogowski coil current probe method. It minimizes waveform distortion. For voltage measurement, there are passive probes, active probes, high voltage passive probes, high voltage differential passive probes, high voltage differential probes, and optical isolation measurement method. For current measurement, there are Rogowski coil, current transformer, Hall element plus current transformer, power measurement shunt resistor, surface mount shunt resistor, and coaxial type shunt resistor. The current waveform measured by a coaxial shunt resistance method increased waveform distortion a lot due to the inductance of a wire and shunt resistance. Even with the current transformer type probe, the waveform is greatly distorted due to the length of the current bridge. Measurement using a combination of the current transformer and the Hall elements also causes large waveform distortion due to the wire length of the current bridge. The best solution is a 100 MHz Rogowski coil current probe. It improves. As you can see, the current distortion is much less than the others, and it captures a waveform that is very close to the original current waveform. With a single high voltage passive probe, the waveform distortion can be decreased by keeping wire length short as much as possible. The waveform distortion is large when measured with a 100 MHz voltage differential probe. Therefore, measuring with the 100 MHz differential probe twisted its probe leads. Waveform distortion seems smaller, but the fall time is slower. For the GaN and SiC switching measurement, an isolation oscilloscope could be used, but the capacitance between the channels affects to the result. The optical isolation measurement shown down below is an ideal method for this case. There are two methods. The one is optical isolation system with a 100 MHz Rogowski coil and high voltage probe. The other is differential current probing method. First, isolation system with 100 MHz Rogowski coil and high voltage probes. Please look at the picture on the left. Waveform distortion is very small, and the switching loss waveform has captured completely. Next, the method using the differential current probe. Please look at the figure on the top. This is the waveform measured by this method. The waveform distortion is very small. The figure down below shows the waveform using a single current probe. As you can see, the waveform distortion is large. In conclusion, when you attach your probes on the DUT, keep the wire length short as much as possible. Keep the probe away from the noise source. Skew the voltage probe and the current probe. And today's main topic about an ideal solution of the reliable measurement of the switching loss of SiC and GaN devices in a small space are measuring by the optical isolation system with a 100 MHz Rogowski coil and high voltage probe, or differential current probe method. A list of works cited is below. This presentation is published by R.Nagahama, translated and voiceover by Rika Miyoshi. For more information, please go visit our website if you haven't already. Thank you so much for taking your time to join today.